Okay, dear students, so welcome to this video. In this video, we are going to learn about gravitational field lines. Now, what are they? Okay, so try to understand this concept first. Whenever there is a field, now I'm writing field here because there are three fields for which all of these things are similar. Gravitational field, number one, then electrostatic field, and then the magnetic field. They were discovered in this order. Gradually, people found that there is a similarity between all these field forces. Okay, so there are some methods to study all of the fields, and we would be applying all of the methods in the gravitational field first, and then when we will go for D2, we would be learning about the electrostatic field as well as magnetic field. At that time also, we would be doing the same thing. So I'm going to draw a complete table now. It's a very important video. Listen to this. So this field can be studied in three ways. Now the first way is that we first talk in the terms of forces. Now, I've already told you about the gravitational field and the Newton's law of gravitation, and the force here was taken to be F G is equal to gmm divided by r square. This was the force, the gravitational force. After that, what we did, we converted it into gravitational field intensity or the gravitational field strength. Now, which in the gravitational field, it should be written as capital I, but that is not used as a symbol for IB physics books. So they are instead using G only, but that is really contested, I would say. But still, okay, fine. IB physics books are doing like that, then you can do it like that. So I is this, and this I was defined as force per unit mass or force experienced when this mass is replaced with 1 kg. So your formula reduces to G capital M divided by R square. Now this is called the gravitational field intensity or gravitational field strength. I believe you know what I'm talking about. The students, those who know what is electrostatic field, I'm just giving you a hint here. We would be doing that in detail in D2. This force is still F, it becomes the electrostatic force, and this, the electrostatic field intensity, is written as capital E. Do you remember it? Like it will be written as capital F, the force, and the same thing is written as capital E. So if you know what E is, you can relate these two concepts. But we would be relating these two concepts later in D2. So for this time, I will restrict myself to gravitation. So this is the gravitational field intensity, which is Gm by R square. Don't get confused. There is a square in the denominator. This is force. The second method to study everything about a field is to talk in the terms of energy. Like for example, we did in the topic 2 for old syllabus, and we did that in topic A for the new syllabus. In A3, we did about like work energy theorem, the same thing. Like we were using SWOT equations, and then we were doing the same question with the help of energy. Same thing happens in these cases also. Now, this is laws of motion given by Newton. Now we are going into energy. So the second method is that we first define potential energy. We are going to do this in couple of next videos. We will complete this part. The potential energy is written as, there is a formula for this, gmm divided by r, and there is no square in the denominator, and it is always negative. So these 2 points you have to remember. This is the gravitational field, then this formula is correct, otherwise not. So the potential energy is negative gmm by r. We are going to see it later. This is basically the HL part, I think. So this moves next, and what we do here is again m is equal to 1 kg, or we start talking in the terms of potential. Now the potential is V, so we would be doing it in HL. The potential is when you take potential energy per unit mass. So this m is going to be removed from this. It will become negative gm by r. Now this is how you define potential. We would be doing the potential energy and potential in details in coming videos, so do not worry. I'm just going to give you an overview of the complete topic, like how are we going to proceed. So these two are already over. This one and this one we have already done. Now there is a third thing that we have to do. There is a third method also. And the third method is the field lines, whether it be gravitational field lines, electric field lines, or it be magnetic field lines. All the fields, they are imagined in lines. So that is the field lines. And along with that, you have equipotential lines. So we have completed forces. So we would be doing next the field lines in this video. Once we will go for potential energy, then we go for potential, and only then we will talk about equipotential lines. Okay. So after when the topic ends, everything will start making sense to you. I believe like you might be feeling overwhelmed that okay, there are too many things now. You can cut the things, like you can leave some videos and you can do whatever you want to do. But as a teacher, I have to give you 100% here. That is why I would be giving you 100% on this platter, and you can eat whatever you want. Okay, so let us now talk in the terms of what is electric field lines, gravitational field lines. Okay, now what is gravitational field line? Gravitational field lines, or for that sake any field line, whether it is electrostatic or whether it is magnetic, it is a graphical method to imagine the field which is otherwise invisible. Getting my point? Now, this is definition given by me totally, so don't write it into any examination or something. This is the graphical method to imagine the field which is otherwise invisible. Like if I talk about like there is a Wi-Fi router here, so if I ask you like how the Wi-Fi will actually be looking like, so you might say that the Wi-Fi is going like this, isn't it? Like this is how the Wi-Fi goes. So these are the lines that are defined as the Wi-Fi field lines. So similarly, we are defining the gravitational field lines, we are defining electrostatic field lines, we are defining magnetic field lines. There's so many field lines. Okay. Now, the actual definition which is given in the books and which you can reproduce in your examination if asked. What is that? The curvilinear lines, the tangent to which at any point gives the direction of the field at that point. What do you mean by that? It means that if there is this kind of a gravitational field shown, or this kind of a electric field is shown here, so the tangent at this point, like at this point, the tangent is pointing in this direction, but at this point, you can clearly see the tangent is in different direction. At this point, the tangent is still having another different direction. So at each and every point, there is a different direction of the field, gravitational field, electric field, or magnetic field. So all these points, like what is the definition? These are curvilinear lines. Like it could be curved, there could be linear lines. The tangent to which at any point gives the direction of the field at that point is called the field line. So gravitational field lines can be defined as the curvilinear lines, the tangent to which at any point gives you the direction of gravitational field at that point. It is like that. Okay, so they are shown like this. Now, what are the features of gravitational field line? Now, this is very important. Gravitational field lines. So, point number one, what are the gravitational field lines? So, point number one is now they are they never intersect each other. The first point that you need to note is they never intersect each other. Okay, because If they ever, like, we imagine that there is another electric field line which is going like this, or gravitational field line, so at this point there will be two tangents in this direction as well as in this direction. The field cannot have two directions at the same point. So that is why we just assume this assumption, because these gravitational lines and all that do not actually exist. This is just byproduct of our imagination. So we imagine that there are lines. So we will say that okay, fine, these lines are not never going to intersect each other, because if they intersect each other, it is fundamentally against the definition itself that at one point there has to be one direction. So that is why they never intersect each other. Now, point number two that you have to note here is that they always start at infinity. They always start at infinity, because the gravitational field lines are always, like, gravitational field is always attractive. They are always going towards the masses. So if I say that there is a mass, like let's say sun, or this central mass, the gravitational field lines will be going into it. How is gravitational field line defined? The another definition is that if you are leaving a mass here, the mass will follow the gravitational field line into the gravitational field. Okay, so even if there is earth here, so their gravitational field is also attractive, so it is also looking like this. If you're talking about moon, so it is also going like this. So they're always going towards the masses. So from where are they coming? We don't know from where are they coming, but they're always going into the mass. So from where are they coming? We will say they are coming from infinity. Okay, so they start from infinity and end at some mass. And they end at some mass. Okay, and the third point that you can write here is that gravitational force is always attractive. The gravitational force is always attractive. Now, one last point here is that the relative density of the lines depict the strength of the field. What do you mean by that? You see, like let's say if this is one of the field line, this is another, and this is the third one. This is how the field is looking like. So we can have 3 points, like this is the first point and this is like second, but let's talk about these 2 points. Clearly at this point the relative closeness of the field line is more, and here the relative closeness is lesser, like it is less dense, they are farther away. So I can clearly say that at 2 the gravitational field strength is less, so I2 is lesser than I1. So I1 will be more because there are more number of field lines near to it. The field lines are closer together. That is why the intensity is more. And at this point, they were farther away. And that is why we can say that yes, the gravitational field intensity is lesser. This is what happens. This is all about the gravitational field lines. Let us now take two examples that are shown on this diagram here. Yeah. So the first thing is this thing. Now what is happening here is, like, majorly the gravitational field will be looking like this because it is having a spherical symmetry, and all the astronomical bodies are spherical, so they would be looking somewhat like this. So if you leave a mass here, the mass is going to follow the gravitational field line itself, and it is going to fall on the surface of the planet. Okay. Point to be noted, at this point and at this point, if you are going to compare these two, here the relative closeness of the field line is more. Here the relative closeness of field line is lesser. So clearly at this point, the gravitational field intensity is more. And obviously it will be more because it is near to the planet now. So gravitational field intensity is more, and at this point it is lesser, no doubt about it. And moreover, it is farther away. The density is lesser here, the density is more. That is why it is more. Even that point is also clear. Now a point to be noted, at each and every point, if you see, the magnitude is different for the magnetic field, as well as the direction is different. So such a gravitational field is actually non-uniform. So this is how we show a non-uniform gravitational field, that even the magnitude is not same, even the direction is not same. So this is an example of non-uniform gravitational field. But if on contrary you talk about another kind of a field, like let's say this, in which there are only straight lines, and that even at a equal gap like this is a fair example of uniform gravitational field. What do you mean by that? These lines should be in the same direction and they should be equidistant. It means that whether you talk about this point or whether you talk about this point, the gravitational field intensity is not changing. Like for example, you talk about the surface of the earth. Do you think that the gravity will change if you're changing from this point to this point, provided that the height is not much? Obviously, so here also the gravity is 9.8, here also it is 9.8. But in this case, if you talk about like real large distances which are comparative to the radius of the earth, we will clearly find the gravitational field to be looking like this. So that will become non-uniform gravitational field. In this case, it will be uniform gravitational field. So this is what is there, like this is point number one, this is two. So the intensity one is equal to intensity two. This is called a uniform gravitational field. Okay, dear students, so this is Professor Vom. Thanks for watching the video. Please do leave your feedback in the comment section for this video particularly. I want to see like what is your feedback on it, on this video. That is very important. Okay, dear students, so all the best. Bye.